Hello. Okay. Today I'm going to talk about making an Apple III arcade game. So that is the plan. The Apple III is sort of like a supercharged Apple II. It has various kinds of improvements. It has more RAM, 128K to 256K, or even 512K if you used a third-party RAM enhancement. It runs at 2 megahertz. It has a built-in serial port, which you can use and you can use a silent type printer built in. It has RGB output. It has 6-bit audio. It has a clock nearly built in, custom text character sets, built-in disk drive, and chainable others, better keyboard, numeric keypad, 80 columns, lowercase, new graphics modes, and an emulation mode for Apple IIs. Last year I talked about the emulation mode. So the thing about the Apple II, or the Apple III, is that it seems like it would be pretty great for writing games. It has a lot of actually new sophisticated stuff. So it has interrupts, a nice interrupt system, vertical blanking, and more. It has a thing called smooth scrolling that I will talk a bit about, hard scrolling in hardware. 6-bit audio. It has 1.4 megahertz speed is actually a little bit closer to the actual speed. We'll talk more about that. And more memory. It has this ability to move the zero page in the stack. It has customizable text fonts, which means that you can basically make sprites out of text. And it has a bunch of new graphics modes. So 140 by 192, 16 color high res. That's the sort of flagship mode. There's also a 560 by 192 black and white only super high res mode, and color text mode. So seems like it would be pretty great for writing games. But there are only a very few games available for it. So basically there's Atomic Defense, which is a missile command game. And I don't actually know even if this was released. It's kind of like might have been Apple internal for all I know. It was written by Andy Hertzfeld, and it actually kind of, in a sense, has the same goal that I have today, in that it's kind of a tech demo. It's showing a bunch of stuff like the smooth scrolling and that kind of thing. And actually, Rob Justice did a disassembly of it, which was very useful in getting started in this project that I'm doing. Another game is Sandman, which is a Pac-Man clone that was, I think that was released by On3, but it's written by Melvin Estrahan. And, so essentially it's a Pac-Man game. And it really looks quite smooth when you see it running. But anyway, there really aren't many. Now, one of the primary things one of the things that people talk about with the Apple III is that it has a character set in RAM. So you can customize the fonts. And what that means is that you can animate things really, really fast. You can change 56 pixels with a single write to memory because it's an entire, the entire character goes in at once. So you could get an entire horizontal 280 by 8 band down with 40 writes. So that gives you some sort of quick animation options. And the on-off colors. So basically when you have a foreground and a background color, for all 56 pixels can be set with a single write. So you can change the colors also very quickly if you're using the color text. So you could even write passable games in Business Basic. They're just text games, and there are a couple of these. So Captain Magneto is maybe one of the more famous ones because that actually got a Mac port later. But it was originally on the Apple III by Al Evans, and it's kind of Ultima style in a way. You run around a text map, and you have a little character, and so forth. There's Apple Chomp. I think I'm not sure actually what the source of this is. I think that was on one of the Washington Apple Pie discs, but that's a little Pac-Man game. You can see it's very evidently in text characters, but so you can make text-based games. There are some of these. There's a very famous demo by Andy Hertzfeld on the Apple III system demonstration disc, which shows these running horses. It's basically animated horses running, and this is all done with the character sets too. So it's very smooth. I probably could have played it, but I'm not going to. So here are 3 frames from it, but you can sort of see how it works, right? and it looks very impressive. How can so many pixels move so quickly, right? Okay, so here's the plan. I thought, well, so the deadline for session submissions this year came up, and I thought, well, I should really submit something, and I should even do something about the Apple III, because like, who else is gonna? So I said, all right, well, I know the Apple III can do all these fancy things, and nobody's used them, and I would like to know how to use them, and I think it could work out pretty well. So I will write an arcade game in assembly language using the new graphics modes and enhanced features and so forth. That's the plan. Of course, I haven't written anything in assembly language on the Apple III before, and I hadn't written any arcade games, and I didn't actually really know how any of the graphics modes or enhanced features of the Apple III work. So this was a nearly foolproof plan. Okay, so what I'm going to basically talk about here is the basic plan of the game, and screen splitting, interrupts, vertical and horizontal blanking, dealing with the memory in the Apple III, the new graphics modes, smooth scrolling, custom character sets, interrupt-driven audio, and that'll be basically that. Okay, so first step: what kind of game would actually make use of the things that I have available? What I want to demo the tech. What could do that? So what I ended up with is something that would split the screen into regions. So that way I could use multiple graphics modes at once. And I'll talk about how the screen splitting could work. But so one mode would be in a band near the top, the next mode would be another band a little bit lower, and so forth. That would allow me to use all these new graphics modes. And I want some sort of vertical scrolling to happen, so I can use this smooth scrolling. That'll be something that it can move things much faster than if they had to be drawn. And I want to use some custom character sets to fake fast graphics, and I want to use the audio DAC for effects. So what I settled on was a kind of a game. I ended up calling it Disc Hero. Don't know, not sure it's a great game, but the idea is that there's a map, and it has walls in it, and scattered around in the map are discs. There are discs of varying values. There are four different types of disc, and your goal is basically to go around and collect them, right? So the idea is, I somewhere in I even made a little like flux image icon and stuff, but I didn't end up using it in the game I produced. But anyway, the idea is you're going out and you're trying to exhaustively image the discs. You're not under any direct threat from anyone in the game, and you're not actually trying to eliminate anyone in the game. You're just trying to collect things, and the antagonists in the games are the hoarders. And so what they do is they run around and they grab the discs, and once they have grabbed them, you can no longer get them, right? So that's the basic idea, and it has a sort of a Dung Beetles like vibe to it. So there's a big map in the background. It'll scroll around. You still can't see all of it at once, but so it'll scroll vertically. You can see all of it horizontally, and then there's kind of a zoomed in section in the middle, and that's sort of where the play field action happens. And so that the zoomed in part is going to be the text mode part. The map in the background is going to be the high-res that scrolls, and there's color text all around. And at the very top, I've got I have a super high-res black and white band at the top. I didn't know what to do with that, so it just makes little splashes whenever the numbers change in the disk inventory. Okay, so that's the game. Here is a MAME screenshot of the game, and actually I can now pull that over. Here is MAME actual. Let's see. So MAME actual. This is the game running in MAME. I'm looking at it over here. So here it is. It scrolls around. You can see the numbers increase. You can drive around picking up discs. The hoarders will also be trying to get these discs, and one thing that you can see is that it scrolls faster than you would expect on a 6502 of this sort, right? So, okay. Anyway, that is the game. Let me come back to this, right? Okay. I might also point out here that the colors in MAME actually look quite a bit different. from what we see on an actual Apple III. So I've got the screenshot of MAME to the left there, and actual Apple III Plus running this on the right, and you can see that it the colors are better on the real Apple III, but they're also different on the real Apple III. So like the little Disk Hero label up at the top is actually almost unreadable on the real Apple III. But anyway, so this is that's the game that we're building here. Okay, so now the way this is set up is that there are these bands, and each band has a different display mode. So the very top one shows the splash effect when the inventory changes. Then there's a text region that shows the score, high-res regions that show portion of a larger map of scrolls. The text playfield has custom characters that are used as sprites, and I never quite figured out what to do with the medium resolution thing at the bottom. So if you look at the screenshot, I've just put like grass down there. Okay. Now let me talk a little bit about screen splitting and how that's supposed to work. So one of the earliest things that I ever encountered with the Apple II was this article in Soft Talk by Bob Bishop called "Have an Apple Split." It's a really great article. You should read it if you haven't. But so what it essentially it talks about, it sort of leads off by saying, if you read the Apple II manual, it says, here are your graphics modes options. These are the only ones that you have. One of them is you can have graphics at the top and a little text mode at the bottom. Otherwise, you can have like high res or low res or whatever. And the premise of this is to basically say, well, if you think about how the sort of actual hardware of the screen drawing works, this picture is drawn by a beam that goes, across the screen, then back to the left, and then across the screen, and across the screen, each for every line. Then it gets to the bottom of the screen, and then it has to go back up to the top. And so there's this little period of time when nothing is being drawn to the screen. So it draws a line, and then there's nothing happening on the screen as it returns to the original side. Draws, and then when it gets to the bottom, nothing is being drawn while the beam moves back up to the top to start again. And so these are the blanking intervals. And so the horizontal blanking interval is one where the beam is going back horizontally to start the next line. And the vertical blanking interval is when the beam is going from the bottom back up to the top. And so what Bob Bishop figured out basically is that we can not only figure out we know the timing of this. The timing is exact to the CPU clock. But we can also figure out by doing this little trick of reading the video memory as it's going out, we can figure out where it is and split it in the middle. So the article is basically talking about how you can on an Apple II, leave it in text mode until the beam gets halfway down, and then switch it into graphics mode and have graphics at the bottom or whatever. It's a little difficult on an Apple II because you don't know when the vertical blanking is, so you have to do these things to try to detect it, and then you have to count cycles. You can do nothing but present the video. I mean, you have to be just counting cycles and switching at exactly the right moment. What the Apple III provides is actual interrupts. So here I have a little picture of how the blanking is supposed to work, and so we know how long everything is. It takes 40 cycles to draw a line, and so that basically corresponds to one column per line. So either one text character or one group of 7 high-res pixels. Then it takes 25 cycles to do a horizontal blank. So there's 65 cycles per line, and then there are the equivalent of 70 lines of drawing time to get back from the bottom up to the top. The vertical blank is 70 lines worth. So on an Apple II at 1 megahertz, that's 4,550 cycles. So we can do this. On an Apple II, we don't have any signal of when the VBL is, but we do on the Apple III. The Apple III has interrupts, a fairly sophisticated interrupt system, and in fact, it also has horizontal blanking interrupts. So this is going to be great. This is going to be easy. Okay, so the way all this stuff works is that it's a lot of this stuff is controlled by two versatile interface adapter chips, 6522 VIAs. They deal with most of the interrupts, most of the memory banking, most of the zero-page placement. They're pretty general-purpose devices. They have timers and counters and I/O registers, and the Apple III connects these things to specific, aspects of its hardware. And the way you talk to these are with the addresses FFD something and FFE something. So there are two of them. They occupy those 20 spaces on the address bus. I had no idea even what this was before going into this. So that is also was also a trick to try to figure out how you deal with a 6522, what it is, because it has sort of a well-defined property. It's not an Apple III thing specifically. The only thing that is Apple III specific is what the inputs and outputs and timers are connected to exactly. So there's one input on this chip that's connected to the keyboard, and so when the keyboard goes, that will generate an interrupt and so forth. Okay. Almost all of the information that there is and that I use for this comes out of this Apple III Level 2 Service Reference Manual. It's pretty much the only detailed reference to how all this stuff works. It's pretty informal. I don't think it was even final. It was not available to regular people in the 1980s. It was kind of like semi-internal. So that may have something to do with why nothing was written, because there was no way to figure things out. I had to spend a lot of time figuring out how all this stuff worked. And again, Rob Justice's disassembly of atomic defense was a huge help in this. Okay, so we'll starting with the screen regions and interrupts. So the way the interrupts work, this again just general 6502 property. FFCD is the interrupt request vector. So when there's an interrupt request, the processor will jump to there. Will move the processing to FFCD and execute whatever's there. So what you want to put there is jump somewhere. And so if we jump to our own interrupt handler, then we can sort of deal with the interrupt as it happens. If you're going to do this, you need to save the state and then restore the state, because your program is doing something else, and then suddenly you're running the interrupt handler, and you want the something else that your program is doing to be able to continue when the interrupt handling is done. So the first thing you need to do is save the state, and then figure out like what interrupt was called. Was it a keyboard? Was it a vertical blank? Whatever. And so you can read FFED to find out what happened on the EVIA, and if you write there, that'll clear the interrupt flag. The relevant interrupts we have are horizontal blanking, which is 20, vertical blanking, which is 10, keyboard, which is 1, and timer, which is 2. And most of the numbers that I say are in hexadecimal, so that's 20 hexadecimal. Okay, so the thing is, it takes time to save and restore the state. So the transfer x to accumulator, accumulator to x, y to accumulator, accumulator to y, each of those take the smallest amount of time a 6502 instruction can take, which is 2 cycles. Push accumulator to the stack is 3, pull accumulator from the stack is 4, return from interrupt is 6. Right, so it takes a little while to get into the interrupt processing. Horizontal blanking occurs every 65 cycles, and you have 25 cycles when the blanking is actually happening. Right, so it drew the line, it hit the interrupt, and 25 cycles later, it's going to start drawing again. If it's taking you 6 cycles just to return from the interrupt, you can see that this is going to be a problem. It's basically unworkable to just sit there and count horizontal blankings and switch graphics modes whenever you reach the scan line, because by the time you're ready to switch, the blanking is over, and you've missed several. So what you can do, though, is that the VIA actually can be set up to trigger not on every horizontal blanking, but count a certain number of them and then trigger. So you can say, give me an interrupt every 8 horizontal blankings, and that will leave you time to restore the context after switching modes, and still leave time to actually run the game when the interrupt is not being handled. So so that's what I've done here. I've basically split up the screen into bands of 8, and those are the only places where it can switch. So it's gonna come in with an interrupt every 8 lines, and see if it's supposed to be switching modes at that point, and if not, it'll return to running the game. Okay, so the Apple III runs its 6502 at 2 megahertz, sort of, sometimes. Actually, what it does is it runs at 1 megahertz whenever the video memory is going out, and that's even so. The processor can be set to either 1 or 2 megahertz, but even when it's set to 2 megahertz, when the video memory is going out, it's running at 1. There's 192 lines of video display. They have 65 cycles each, so that's 12,480 cycles while it's drawing the video down. Then the vertical blanking takes the equivalent of 70 lines, which at 1 megahertz is 4550 cycles. If it's running at 2 megahertz, then that's about 9100 cycles. So what that means is that the 73% of the time, the Apple III is running at 1 megahertz, and 27% of the time during the vertical blank, it's running at 2. So it's not really running at 2 megahertz much of the time. I think it winds up being something like 1.3 megahertz or something is the average, but it's hopping back and forth between the two speeds. The problem is that MAME, the only sort of viable way to emulate the Apple III at the moment, does not emulate the downshift in speed while the video is being drawn. So if you set it to 2 megahertz in MAME, it's just going to run at 2 megahertz. So on a real 3, you want to shift the video mode between 65 and 80 cycles into the interrupt processing. That'll be during the horizontal blank after the one that triggered the interrupt, right? MAME is going to run twice as fast. It's not going to slow down at that point, and so it's going to get through 130 to 160 cycles in that same, sort of drawing time. So it's very easy, as I, ask me how I know. It's easy to wind up with something that looks fine in MAME and then gets the screen splits all wrong on the real hardware because it's missing horizontal blankings. So in order to get something that runs well on both MAME and real hardware, you have to switch fast because they get far apart pretty quickly. And it's also fairly easy to fool yourself into thinking that the game runs fast enough when you're developing it on MAME. So very important to set the next 8-line horizontal blanking timer immediately in the handler. So what I did, this is a picture of the interrupt handler that I have, and I don't have a way to actually point to the screen. I could use my finger, but anyway, that's not worth it. So this I've shown a little bit of the code here. What I've got, I am trying to reset the timer before even MAME could get through a horizontal blank, and I managed to do it in 30, it looks like, by sitting there and counting and not even saving the context until I know if I have to reset the timer. So I save the minimal amount of context, check to see if it's a timer, reset it if I have to, switch the modes, and I switch the modes in a sort of a special way where basically record the mode reference that it uses, like when it's saying this is the list of modes it's going to go into. The number I use to refer to each mode is actually a branch distance. It's like a jump table. So instead of saying like mode 1, 2, 3, and then look up how far I need to jump for mode 1, mode 2, and mode 3, I say this is like mode 24, this is mode 30, this is, and the 24 and 30 are exactly how much it needs to branch. When you look at this, you think, well, you could push stuff to the stack. Why are you doing this, or why are you writing to an absolute address? And like I'm stashing the accumulator in a 16-bit address when it would be faster. I'd save a cycle if I stored it in the 0 page. Why don't I do that? Because the Apple III can have a repointable 0 page in stack. So unlike the Apple II has a 0 page at 0. That's a good sort of a sensible place for a 0 page, and the stack at 100 immediately next to the 0 page. That's sort of a standard 6502. That's the way the 6502 operates. But the Apple III allows you to designate any page as the 0 page and the stack. So the 6502 can refer to any address in a 64 K space using 16-bit addresses, 2 bytes of addresses. But there are 2 special pages, and that's the 0 page and the stack. The 0 page is, there's a special set of faster instructions that can access the 0 page because it only takes 1 byte to refer to the address. So those are faster. That's the advantage of using the 0 page addresses. And the stack is a last in first out data store that can stash information pretty quickly. It's not as much faster than storing to absolute addresses as one might like, but it is it's still fairly quickly. It saves program space at least, if not cycles. Okay, so on the Apple III you can specify which page is the 0 page. It doesn't have to be 0, and you can use that to interact fast with like graphics memory, which I'll get to. But what that also means is that I can't, in the interrupt handler, rely on putting the stack in the 0 page being in any place I know. So this is the way it works. To set the 0 page, you store the value in FFD0. That will tell the Apple III what to report is the 0 page. And then you have a choice about the stack. It can either be adjacent to the 0 page, so it's the 0 page exclusive or 1. So that'll wind up being above the 0 page you picked when it's odd, or if the 0 page you picked is even, it'll be below. The other option is you could just have it at 100. So it could either follow the 0 page to wherever you sent it, or it could just be at 100 while the 0 page is off wherever you said it was going to be. If the 0 page is in video memory, then it's more sensible probably to pick true 100 for the stack, because otherwise the alternate stack would also be in video memory. And so that keeps you from doing a fair amount of things, because like even JSR and RTS mess up the stack. So if the stack is on your screen, you will see your screen messed up. How you choose the stack placement is one of the bits in the environment register at FFDF. So just a quick note about pushing to the screen. So if you want to store a line of A's, A characters in the first text line, which is in memory at 400 to 427, then the sort of simplest way to do it would be to in the sort of the upper left box there, load the accumulator with A, load X with 27, that's the last column, store that A in 400, index X, decrement X, and then keep going until X rolls off the end. And that'll to do that, that'll take 364 cycles to fill the line with A's. If you point if you point the 0 page at 400, then instead of storing at 400x, you can store at 0x. So the box sort of lower middle there, I'm first pointing the 0 page at 4. And I'm counting the cycles for that too, because that seems fair. Then same logic, except instead of storing at 400x, I'm storing at 0x. So instead of taking 5 cycles to store, it takes 4. It repeats, and it does that. It saves that one cycle 40 times. So that gets me to 330 cycles. So quicker, 30-ish cycles quicker. And if I wanted to use the stack, the box sort of furthest right there, we can set it up so we point the 0 page at 5, and pick the alternate stacks, which is going to wind up being at 4, and then we use the same thing. We load the accumulator with A, we load X with 27, which is the column, we transfer X to the stack pointer, so we're going to start pushing onto the stack at 27, and then we push decrement until it runs off the bottom, and that gets us to 300 cycles, including the setup. So it's quicker. If you can point the stack at the thing you want to fill, and it's something easy like that, you can save quite a bit. Every write is 2 cycles faster. So anyway, that's the advantage, and that's one thing that the Apple III can do that the Apple II cannot. So that's one of the things I wanted to play around with. I do use this in various places, but what that means is that when an interrupt arrives, I don't know where the stack or 0 page are, and they might be on the screen. So if I'm going to save the state to the stack, I might just be messing up the screen at the same time. And it would cost me more to set the stack and 0 page to a known value and then restore them to whatever they were, than it would to just use a 16-bit address. So that's why I used a 16-bit address. Okay, here's the memory. The memory layout. So 6502 can see 64K at once, but the Apple III has more space than that. And so the way it handles that is that there's a region in the middle that's bank switched. So from 2000 to A1000 is 32K that can be any of a number of different banks. So and how many different banks depends on how much memory you have. So 128K has I think 3, and 256 has more, 4 or 5, something like that. Anyway, so you can that's how it addresses the more memory. It bank switches the area from 2000 to 8000. The way you control that is you put the bank number in the bank register, which is FFEF. So the sort of easy, straightforward way to deal with this banked memory is to pick which bank you want and just manipulate the memory in there. So swap the banks if you want to manipulate other memory. Problem is, where is your program? So the text memory lives from 400 to C100. There's stacks and 0 pages and stuff that's also down there below 2000. The graphics memory lives in 2000 to 9FFF in bank 0 only. So if you're going to be putting pixels on the screen, it's going in bank 0 in that space. And then SOS claims 8000 up. Like, you're not supposed to use 8000 up because it reserves that space. It turns out that actually it doesn't, in fact, start until B800. So you're safe between 8000 and B800 until the next version of SOS, which means you're safe. But I mean, like, it is kind of tricky to figure out where your program goes. I mean, what you really need to do, I guess, is normally have a little loader, a little switcher or something in the low memory below 2000, and then your main program in a bank, and you sort of jump back and forth to the switcher to get the banks in and out. But you sure don't want to switch the bank out if your code's running in it. So there's one other way that you can get at memory, and that's I'm calling it extended addressing. I'm not sure if I made that up or not, but it's a addressing trick that lets you read or write data in other banks. So the 6502 fundamentally only addresses 8 bits, but what the Apple III will do is it will look at what the 6502 is asking for, and it will say, I'll give you this instead. It'll fake out the 6502 by giving it something other than what it asked for. So if the 6502 asks for a byte at 1000, the Apple III could check the bank address, grab the 1000 byte, and hand it to the 6502. 6502 just thinks it's 1000. Actually, I guess that would be 3000. It doesn't know anything about banks. It asked for 1000 and it got 1000. And the Apple III itself was the thing that said, oh, but you're looking at bank 3, so 1000 corresponds to this. That's also the same thing that relocates the 0 page and stack. The 6502 says, give me 27 on the 0 page, and the Apple III says, that's over here, and hands that back. So it's the same kind of thing. Basically, there's an intercept between the RAM and the CPU. So the way extended addressing works is that if your 0 page is pointed at 1A100, which is actually where SOS by default puts you, then if you store the lower 16 bits of an address at a pointer and 0 page, say 20 and 21, right, and then store a bank address in the 1600 page, which is parallel to the high byte of the pointer, so it's 1621, then if you use the addressing mode indirect 0 page indexed Y, that will interact with the memory thus designated only in that indirect 0 page indexed Y mode, though. So here's a little picture of that. What I've done at the top in these two blue boxes is I'm setting the 0 page, right? Load 1A, store FFD0, and then I'm setting a pointer at 20. So load 0 in the left one, load 0, put it at 20, load 90, put it at 21. So now indirect address 20 points to 9000. And then I put an 82 in 1621, so that's 21 plus 1600. 82 refers to bank 2. Load Y was 0, that's the index, and then I load indirect from 20 indexed Y, and that will return to me byte 9000 when bank 2 is switched in. I hedged there because I probably should have done the right box first. So in the right box, it's all the same, except that what I'm putting in the pointer is 1,000. So 20 gets 0, 21 gets 10, right? So it's going to 1,000, and it's looking in bank 3. And so if I retrieve byte 1,000 of bank 3, that's in fact the same actual byte as retrieving byte 9,000 of bank 2, because byte 9,000 actually isn't in bank 2, it's in bank 3. So what this means is that when the X byte, the thing in 1621, says bank 2, that means that the addresses from 0 to 7FFF are in the bank we referred to, and then the addresses from 8,000 to the top are in the next bank up. So if you have bank 2 at the bottom, bank 3 is right above it. If you have bank 3 at the bottom, bank 4 is right above it. So these two boxes actually are retrieving the same byte. One is calling it the 1,000 byte of bank 3, and one was calling it the 9,000 byte of bank 2, but it's the same byte. If you have bank F, 8F, if you put 8F, in the bank, the X byte, then that will, instead of doing any of this bank stuff, it'll put bank 0 in the sort of regular place in 2009 FFF. And then have all the regular unbanked memory around that. So that's actually pretty useful for well, I guess I use that for putting stuff in the graphics page, but also it's the only parallel way to access the first 100 bytes of bank 0, because if you were to try that, you can't bank it in and then refer to that, because if you do, it's going to go to wherever the 0 page is said, because anytime you try to read from 0 to 100, it goes to the 0 page, not whatever the indirect addressing tells it. Okay, anyway. There's a little thing, I don't know if I should even get into this because I'm running very low on time, but John Jepson wrote an article in Soft Talk called Bank Switch Razzle Dazzle, which talks about sort of why you have this 1601 pointer, and it's actually pretty clever. But the basic idea is that it automatically picks up this. So this, okay, if your 0 page is at 1-800 and your if your 0 page is at 1-800, your pointer, your X byte, is going to be at 1600. And the reason for that is actually that it is 1600 is 1-800 exclusive or C100, and that doesn't seem like that tells you anything in particular, except that the reason this works has to do with how the 80-column text mode works. So 80-column text mode takes one set of like the even characters from 400 page and odd characters from 800 page, and then displays them both at once. So in order to be able to do that, it has to pull them both in at once. 800 is 400 exclusive or C100. So what that means is that the hardware, whenever you ask for 400, it's also pulling in 800 because it might need that data. So it has access to both of those things at once. It basically always has access to the thing you asked for and the thing you asked for XOR C100. So if you do a load accumulator indirect indexed Y, it's going to, at 20, then it's going to take the byte in 20 and 21. But as it loads 20, it's going to also pull in C20. And as it loads 21, it's going to pull in C21. Those are actually on page 2 text. It's maybe not super useful, but we have access to all of those addresses. And the thing is, you can point the 0 page to somewhere other than 0, right? So if you point the 0 page to 1-800, it's going to pull in 1-820 when it asks for 20, right? Because when you ask for 20, it's going to pull in 1-800. And then when you pull in 1-820, it's going to also pull in 1620, because that's 1-820 EOR C100. So the shadow system grabs 1620 at the same time, and so it has access to all of these things at once, and so it can use that implicitly grabbed byte to hold the bank that it's going to head. This only works if the 0 page is between 18 and 1F, though, which is a little annoying, because it would have been useful if you could point the 0 page into graphics and then also use extended addressing, but you cannot, because 18 and 1F does not include any graphics. Okay, here are the new video modes. There are several of them. There's a 24 by 80 color text mode with 16 foreground, 16 background colors. There's a 560 by 192 monochrome mode. There is a 140 by 192 16 color mode. That one is the sort of the main high-res mode. And there's a 280 by 192 graphics mode that has 16 colors, but it's constrained. So the way these work is we have the 24 by 40 familiar Apple II mode that has text page 1 at 400, text page 2 at 800. Then we have an Apple III text mode where it uses those same two areas, but one page is responsible for the characters and the other page is responsible for the colors. Both of these can flip. So I don't know if you can read the text on the screen, probably not, but there's a page 1 and page 2 soft switch, which is commonly used in Apple II games to basically smooth out animation. So you can display one page while working on the other page, and then when the other page is done, you can flip them and display the one you've just finished while you work on the first one again. And so many of these, this sort of page flipping is possible in many of these modes. You can page flip normally in the 24 by 40, Apple II text mode. You can page flip in the Apple III mode, but I don't know why you would, because then what that's doing is reversing which page has the colors and which page has the characters. So you can flip it, but why? 80 column text is fairly straightforward. The characters are interleaved. So 400 the 400 page has the even characters, the 800 page has the odd ones. And then there's a black and white high-res mode, which is basically familiar from the Apple II 280 by 192 that has no color artifacting. It's just monochrome. But it has, page 1 is at 2000, page 2 is at 4000. You can flip it just like you can on the Apple II. There is a medium resolution mode. So this is again the same resolution as the Apple II 280 by 192. But what's different about this is that unlike the Apple II, there's on the second page, so 2000 are the pixels like the Apple II, and 4000 are colors, which basically set the background and foreground color. So what color corresponds to a 0 pixel? What color corresponds to a 1 pixel? So that provides a much enhanced color setup. These two can be flipped, but again, not very usefully because it's unclear why you would want to switch between the colors and the pixels like that. So this is the highest resolution 16 color mode that we have, but the colors are constrained. There's super high res, which is sort of corresponds to the 80 column text. This is 560 by 192 black and white in blocks of 7 that are drawn alternately from 2000 and 4000. It just like all of these, it only uses 7 bits of every byte. The most significant bit is not displayed, and in this case, it doesn't do anything. On the Apple II, it's a sort of palette setter, but here it does nothing. So you could conceivably hide information in your graphics page if you're looking for, a place to hide game data or collision data or something like that. I could see that being potentially useful. I did not use it. Interestingly, this one can also flip. So this and usefully. So it's using 2000 and 4000 together to make this 560 by 192 space. But then it also has a full second page from 6000 to 8000. So 6000 is the first set of blocks, and 8000 is the second set of blocks for page 2. So you can do page flipping, and it'll use the entire bank to do it. And then Apple III high-res, this is the most comical. This is 140 by 192, 16 colors, every pixel can be set to whatever. And the organization is ridiculous. So it uses 2000 and 4000. It uses both of these graphics areas. Every pixel uses 4 bits of information. And so you would think actually that you could do this relatively sensibly, except that we always throw away the 8th bit. We never use the 8th bit for anything. We always only use 7 bits. And so the only way to get this information distributed is to rotate the bits around so that byte 2000 holds the first pixel. And it also holds 3 bits of the second pixel. the last bit of the second pixel is in byte 4000. Byte 4000 also holds the second the next pixel, the third pixel, I guess, and like 2 bits of the fourth. The other 2 bits of the fourth are back in 2001, and so it is insane. The way this relatively informal document describes it, it says there are 2 distinct screen pages in this mode, but the mapping of the individual pages is, at first encounter, a bit difficult to master. Good luck. This one can actually also flip, like the super high-res mode. So it can use an entire bank for graphics memory, 2,000 and 4,000 for one page, 6,000 and 8,000 for another. So in the game that I've constructed here, we have video memory for regions, and they're not all coming from the same place because they're different display modes. So almost every other line is coming from the display memory at 2000, and the ones in between are coming from the text memory at 400. So we'll have to sort of keep track of that. And fortunately, the layout of all of the high-res graphics modes is the same in terms of scanline organization. So it is possible to have, in that same 2000 to 6000 area, some lines with super high-res data, some lines with high-res data, some lines with medium-res data. Okay. Scrolling. So the Apple III has a hardware support for scrolling pixels vertically, and I will now describe that. So on the left, I have a picture of what would you need to do if you wanted to scroll, basically, what is this, 16 lines on an Apple II up 1, right? So 16 high-res lines, you want to scroll them up 1. The way you do that is you basically sort of iterate down from the top. You copy line 1 to line 0. You copy line 2 to line 1, 3 to line 2, 4 to line 3, and so forth. When you get to the bottom, you copy the top line 0 of the next group, up to line 7 of the top group, and then you do it again. So copy line 1 to 0, copy line 2 to 1, 3 to 2, and so forth. So if you're going to scroll 16 lines on an Apple II, you need to write 16 lines of data. That is, that seems like, how could you do better? But here's how you could do better. The Apple III notices this pattern. It says, okay, well, if you do this, imagine doing the Apple II scrolling 8 times. So you do it once, everything shifts up once. You do it again, everything shifts up again. And eventually, what you wind up with is line, all of the bottom 8 lines have been copied into all of the top 8 lines. And so what the Apple III does is says, well, if that's the state we're going to end up in, we're going to, copy the lower green line to the, to the upper green line, and the lower blue line to the upper blue line, and so forth. If we're going to end up in that state and we're getting there incrementally, then we could do this. We could save a bunch of time here by allowing it to happen in the steps that are on the right. So on the right, we start with the same box. We copy the second byte down, the 9th line. We copy that up into the 8th line. So, and then we start drawing the pixels. Instead of at the first line, we start drawing them at the second. So what the Apple III allows is basically that for in each line of each group of 8, you can start at any of them. So if you start at 1, it'll draw 1, 2, 3, 4, 5, 6, 7, 0. So it'll draw the 0th line, but it'll draw it under the 7th. And if you start at 2, then it'll do the same thing, except it'll draw 0 and 1 at the bottom. And so the idea is that if you're going to take these 8 steps anyway, you can do them one at a time. So you can just draw 1 line and scroll up. So all we've redrawn is line 7 and scrolled up. And next time we'll redraw line 6 and scroll up 2. And next redraw line 5 and scroll up 3. And eventually, once you've gone through 8 steps, you will have copied the entire bottom block to the entire top block, but you won't have done all the intermediate writes. So that's moving much less data. This is a little bit from the patent that describes it. So the scrolling operation is somewhat unusual in that each line is separately moved up line by line with one line of data being moved for each frame. And it sort of describes how this works. There are basically three soft switches, three inputs to the scroller. And so the scroller can be at 000, which means it's not scrolled, or 001, which means it's scrolled up by 1, up to 111, which means it's scrolled by 7. So the way this works is there are these soft switches. So if you want to scroll to 010, you hit COE4, COE3, COE0. That's the three the 3 bits to 010, and that'll scroll it up 2, right? So it's it's clunky, but it saves you a lot of time. It is hard to get your mind around, so I spent a lot of scribbling time on this. It also only functions for high-res display modes. So there are several different soft switches that determine what the display modes are. There's the 3 here that are relevant: high-res, mix, and graphics text. And those words sound like they mean something, but they don't actually correspond very clearly to what is happening here. And that, well, maybe, I don't know. Anyway, mostly the text modes are not high-res, and the graphics modes are high-res. You would think that the graphics text switch would do that, but no, that is something different. At any rate, the high-res ones are the ones that do the smooth scrolling. The text ones are not, which is a little bit weird, because I would have thought that the reason for doing this would be to allow for smoothly scrolling text, but apparently that is not something you can do. MAME, however, does not understand this. So MAME will do it for text modes too, but it scrolls things sideways in a very strange way. Real hardware does not do this, but it also means that if I want something that's going to run in MAME and on real hardware, I need to turn off the smooth scrolling in the non-high-res regions. Okay. Next bit, custom font. So I created a custom font for this. The idea being that I would have little icons that would run around in the middle, and So I guess one point about this is that the font, I defined the font all in the assembler. So it's possible to just use zeros and ones to draw the fonts, and so I basically throughout all of this project I didn't bring up any editors of any sort. Everything was done in the text editor. So the map is built with just placing boxes that I designed in text around, and the sound is that I'll talk about later is built with just like taking a sine wave, cutting its frequency in half, and superimposing them on each other. But okay, anyway, custom font. The fact that you can change the font is commonly mentioned, but not really how. There's a driver way that can do this. So Apple provides a driver. That's pretty much the main way people do it. There's a way you can get Business Basic to do this, but I'm not using drivers. I'm not using Business Basic. I needed to know how this actually worked. The font data doesn't live in addressable space, so you can't just change it. Otherwise, that would actually be quite nice, but you can't. You have to stage it into some hidden RAM space. So you put it somewhere and then tell the Apple III to come get it. It's not really, I don't really know exactly how this works, but it's fairly clearly leveraging the scan through video memory. So the way this works is that you put 8 characters worth of data into the text page screen holes, and then you turn on the scan font data switch, and then you have to wait for at least one full vertical blank cycle, and then you can move on to the next set of 8 characters. You have 128 characters to play with. The other 128 are just the inverse. Screen holes are, if you don't know, on the text page, every triplet of lines on the text page has a screen hole on the edge, and that's because the text line is 40 characters wide. But every 128 byte boundary is lined up on the left edge. So the first line goes from 0 to 39, now to speaking decimal for some reason. Second line goes from 40 to 79. The third line goes from 80 to 119. And the next thing we do needs to line up with 128, which means that 120 through 127 are not used for anything. Those are the screen holes. They're not displayed anywhere. They're in the text memory space, but they're not displayed. We have 8 of those, and each of those 8 screen holes has 8 bytes in it. So we have 64 bytes free, and whatever you write in here doesn't affect the screen data. So that's where you put the font data. You put the font data there, and then you tell the Apple III to come get it. Okay. Fonts are 7 by 8, right? And again, we throw away the high bit, so it's 7 across, 8 down. You would think a sensible way to do this would be that each screen hole would contain the data for one character. That's 8. It's 8 bytes long. Font data is 8 bytes tall. Or, failing that, that they would be organized down the screen. So with the 8th byte has the all the 8th byte of each screen hole is the data for the 8th character. 7th byte is the data for the 7th, and so forth. That would make sense. It is neither of these things. And not only is it neither of those things, I did not find this information written down anywhere. The monitor ROM does set up the characters when it boots, but it uses a compressed data that it's very hard to understand like what the data is, because it's all compressed into smaller space. So I basically figured this out through trial and error. But in fact, the font data layout is each screen hole contains 2 bytes of 4 different characters. The first 4 screen holes contain the first 4 characters, and the last 4 screen holes contain the last 4 characters, because Apple can always find a way to interleave things just one more level. There are screen holes in page 2, and they are also used. They contain the character number, right? So the character data, pixel data, is in screen 1. The character number is in screen 2. So if you're updating character 1, you have to put 8 ones in the page 2 addresses that correspond to the 8 addresses holding the pixel data in page 1. My guess is that the system is dumb enough that you could actually scatter the character's data around slightly differently, but I can see no advantage to doing that. So I mean, you could conceivably have the last bytes of the first screen hole contain the first line of character 2 and the second line of character 3 if in the 800 page you put a 2 and a 3 there, but it is unclear what that could possibly buy you. So anyway, here's a picture of how this works. Pixels are down. The pixel address screen hole is listed on the left. The characters A, B, C, and D are the characters, the font characters we're uploading. So row 0 of character A is first, then row 0 of character B, then row 0 of character C, and then row 0 of character D, then row 1 of character A, B, C, and D. And then down to the next screen hole, we have row 2 and 3 of A, B, C, and D, 4, 5, 6, 7. And then in the last bunch of screen holes, we switch to the next 4 characters. So row 0 of E, F, G, and H, row 1 of E, F, G, and H, next screen hole, and so forth. And then the character code goes in the screen hole that's listed on the right. So this would have been a very useful chart if it existed sometime prior to 2022. Anyway, okay, so the way this works is you put the data in the screen hole, you touch C0dB to turn on the font trace transfer. You wait for a full VBL cycle, which usually means waiting for 2 interrupts. The first interrupt will happen after an incomplete one. And then you touch C0DA to turn off the font transfer. And anything you don't change stays like however it was set up before, so like by the monitor. So it doesn't hurt anything to leave some characters untouched, and it also doesn't hurt anything to change something twice to the same thing. I mean, so if you need to transfer 9 characters, you can transfer 8 and then change one of them and transfer another 8, except 7 of those 8 were the same one you already transferred. That's fine. Okay. The last major topic is the audio. It's often mentioned, with very little information of how it works, that the Apple III has a 6-bit audio DAC. What is that? Digital audio converter, something like that. Digital analog converter, I suppose that actually is. Anyway, the way this works is that PB, port B, of the eVIA. It's accessed by FFE0, and what that tells us is that the lower 6 bits of what you write to FFE0 go to the DAC. And actually, it turns out that same address, FFE0, is also the place that accesses the horizontal blank. And interestingly, nowhere in this document at all could I find any information about the fact that this is horizontal blanking. You can see on this very screen the only text that even relates to this at all that I could find. It doesn't say anything about that. It just says that PB6 is connected to the IO count line. And it turns out that PB6 is in fact counting horizontal blanks. So you can use the IO count to count horizontal blanks. Anyway, doesn't matter. That's not the audio DAC. This is the same address though. I don't know what an audio DAC is supposed to be. At least I didn't before I started this project. And in fact, now I'm not even sure that I do completely know. But anyway, what are these 6 bits encoding? It seems to me like what they're encoding is essentially an amplitude. And at least it seems to work when I treat it like that. So what that would mean is if you want to produce a sine wave, then you just raise its value up and down in a sinusoidal pattern, and if you do that repeatedly, the frequency will dictate the pitch. So the document that I showed on the previous slide says there are 127 different possible tone combinations, but I can only count to 64 with 6 bits, so it's a typo? I don't know. Or maybe I still am not understanding something about what those 6 bits do, but in any event, the basics of running the audio is pretty simple. You just put the amplitude in that audio register. If you want to have a reasonable pitch and smooth sounding audio, though, you have to do it often and regularly. And, this is great. We have an Apple III. It has interrupts. We can just set it, say, interrupt me at the time that I want the audio to go, and I will provide the audio. Seems great. Turns out, though, not that easy. So here's there's an article on On3 by Al Evans that talks a little bit about this. It's one of his columns, and he was trying to do basically exactly this. He was trying to use interrupt-driven audio in a game context, but what he observed was that the minimum response time to call an interrupt handler is about 160 microseconds, and then another 115 is required to return. It's possible that that's not actually as good as you can get because that may be running everything through sauce. We are bypassing sauce here, but the point is still the same. It takes so long to get in and out of the interrupt handler that even if it's super quick to actually update the DAC, you're going to spend all your time going in and out of the audio handler. You're not going to be able to get a very high frequency, but you're also not going to have any time to run the rest of your game. So he gave up. The guy who wrote Captain Magneto gave up, said, "This is beyond me." Turns out, though, I have something I can do, to sort of factor out that in and out issue, which is that I already have a horizontal blank interrupt firing several times a frame, and so I'm gonna just piggyback the audio on that, since that's happening all the time anyway. And I can just say, also transfer the audio as I'm checking to switch the mode. Originally I had it firing the horizontal blank firing actually only whenever I needed a mode switch, so it would go 10 lines and then 20 and then 10 and then but for the audio we really wanted to fire it more regularly than that, so I've changed it so that it fires every 8, and whether it needs to switch or not, and it will do very little if it doesn't have to switch. One thing this doesn't account for is the vertical blank. There should be about 8 or 9 audio samples pushed out during the time of the vertical blank, and it actually really does sound pretty bad if you don't do that, at least on real hardware. So what I did to account for that is that when the vertical blank is happening, I set up just a timer that goes off at about the same rate, so that it should get us somewhere between 8 and 9 audio samples during the vertical blank before it comes back. None of this is perfect, and I certainly didn't compute it very carefully, so the sounds are a little clunky, but Okay, and then the gameplay, I just had to, to make this actually work, I had to do the technical part, like how do you move, how do you make the hoarders move, how do you keep track of the score. Keyboards can generate an interrupt, so that's a key press will be fairly easy to handle. The whole game is basically an event, sitting in an event loop that just basically waits to quit, and the interrupts are the things that make stuff happen. It uses the vertical blank to generate the game clock that triggers the characters to move. Okay, so when I started this, I didn't really know anything about CA65, but I used that as the cross-assembler. And I used it just from the command line because I was not about to learn how to use Xcode. I may not be using it particularly correctly, and there's probably fancier stuff I can do with the memory and segment configuration. The program's all one binary file, and it's stored on the disk as sauce.interp, which allows it to boot. And we talked about before that even though 8000 through B800 should be safe, even though it's not endorsed by Apple, the program got big enough that I had to start pushing it down, which means, so I think it starts at 9700 at this point, which means that I have to put all the execute once setup stuff early so that it's okay for a bank to switch over top of it later. But all it takes really to make this work is to compile the binary file to something called sauce.interp that has a special header on it stored on a disk, and it'll just boot. So yeah, I mean, I used, for pushing the graphics, I used a standard lookup table for high-res Y coordinates, and then I set the 0 page into graphics memory and then write with graphics memory opcodes, so that speeds up what it takes to put there. I could use the stack. I talked about the stack being faster, but that limits your use of 0 page because the 0 page will also be on the screen. So I think if you're careful and use just 78 to 7F and F8 to FF in 0 page, which are in the screen holes, you might be able to get away with using the stack and some 0 page pointers. But the other thing is extended addressing doesn't work when you're pointed into the graphics memory, because extended addressing requires 0 page to be between 1.8 and 1F. So yeah. The colors MAME produces don't quite match the ones I see in the actual Color Monitor 100. I showed you that earlier. And MAME runs faster, detectably. So the audio tends to sound better in MAME. And I think it's basically, in a sense, it's because MAME is operating too well. It's going too fast. The real Apple III slows down to 1 megahertz 73% of the time. MAME just plows ahead at 2 megahertz, which means that fixing MAME is kind of adding code to make it worse, which I guess is fitting for an Apple III emulation. This is the kind of thing that could always be more finished. It's not bug-free yet. Sometimes it will crash if you're traveling downward, and occasionally, particularly on real hardware, the audio sound effects will overpower the mode switching and get the screen to display garbage. And in fact, actually, if it's in this mode where it seems frozen and displaying garbage but still playing music because the interrupts are still firing, if you turn off the sound, which you can do, one of the first things I added was the ability to turn off the sound. So if you hit S, it'll turn off the soundtrack. If you hit Q, it'll turn off the sound effects as well. Then it often will still be running. So like if you turn off the soundtrack, then you can control it again. It's not crashed. It's just sort of not getting the interrupts it needs. There's not currently a way to win or lose. The hoarders are supposed to head for the disk that's closest to them, but it's not clear that they do that. Actually, I think they're supposed to head for the most valuable disk that's closest to them. But I need to get that to work in order to allow dropping a distractor disk to work. The map may be too large to be fun, so it's possible that I should have levels and start with smaller. And it would be nice to think of something to do with the lower medium resolution region. Right now it just shows a grassy pattern. I couldn't think of a good thing to do with it. It's a very busy screen though, because it's a tech demo. I mean, it wasn't really designed to be like, what's the most fun game I can write? So I wanted to have, super high res at the top, medium res at the bottom, but I don't have anything to display there. So anyway, so that is it. The code will be available on GitHub to look at. It'll be under my GitHub account somewhere. And I'm going to try to see if the MAME in a browser on the Internet Archive will run this. I don't know if Apple III emulation works there or not, but if it does, then that would be kind of cool. I could at least play it in the browser. And I guess part of the point of doing this was to provide an example of how these technologies could be used to help future others or future me, by at least having something that sort of shows how it can be done, so not everyone needs to keep banging their heads against the level 2 reference manual. Okay, that is it for the presentation part. I don't know if I don't know if this is I was thinking back when I thought that this was going to be short, that I would kind of go through the code a little bit and just like point out things that seemed interesting about it. I think that may not be sensible, but anyway, this is the code. There's the header that tells Sauce to basically load this with the when the disk boots. So I didn't change anything here. And in fact, this is copied straight out of the Atomic Defense disassembly. But the first thing it does is jumps to an init, and then includes a bunch of stuff which does things like build the map, build the sound, and then routines that handle the different regions. So status text 40 is handling the score and the inventory. Game move is the sort of main logic of moving, so that moves you, checks checks for collisions in the map, increases and decreases the disk inventory. It figures out where the hoarders are going to move and that sort of thing. That's all in game move. And then game font is where the font is uploaded. That is, let's see. So if here, so this gives a sort of a, the code for actually doing the upload, and then it also contains the data, the font data. I've got dots which indicate basically on the map when you have a particular character, like say I have the hero. Well, that's not a good idea. The disk, right? If I have a disk on the map, then font dots will say that up in the higher res map, it's going to be indicated by an on pixel and an off pixel, and the actual color that's involved is going to depend on what type the disk is. For things like the hoarders, the 2 pixels that represent them up in the high-res map have actual colors, so that the actual colors are 13 and 12, which I think is yellow and green. And in fact, I have 1 and 2 are frames, so it animates between them, and the hands will you can see that they sort of animate back and forth. It's 1 pixel is 12 and 1 pixel is 13, and then they reverse. Then it's 13 and 12. So you can sort of see them. You can see them animating up in the higher region. I've named everything so that I can refer to them. So C disk is just a name that I refer to with elsewhere when I'm trying to. Or actually, that's most useful for the building of the walls. And then the actual character data is here. The character data is backwards. It's not super obvious, but so the stuff on the right is displayed on the left, and the stuff on the left is displayed on the right, and the most significant bit is not displayed at all. Anyway, so it's fairly easy to just modify the font here. So I didn't use any pixel editing program. I just used this. The sound is done. I have a sine table that I just copied out of somewhere. I don't even remember. And then so I just generate this terrible music that it plays. So I've put together a little thing that basically, where is it? Tucson, which basically just takes 2 values and then uses them to superimpose 2 sine waves. So it basically allows for harmonizing these 2 notes. It seemed good enough. And then I have sound effects. So there are sound effects defined. Hero got a disc, so it plays these samples. It'll play a sample up until it ends in a high bit set. So once it hits a minus value, it'll stop. So the way you start this is you basically say starts playing at this. Start a sound effect at the place where FX hero got starts, which is defined as here 1F. So it's going to start at 1F100. So you basically set the player to start playing the sound effect at 1F100. If the hoarder got it, you play the sound effect at 1E100. If you tried to drop something you don't have, then it's gonna then you start the do sound effect at 1D100, and if you drop a disc, then you start the drop sound effect. So anyway, yeah, I mean, I guess there are lookups. Random numbers I took from Doom. The random numbers is a list of numbers that are therefore not random, but anyway. So anyway, I guess that's basically it. Maybe the most, what is happening here? Okay. One of the most, well, there are two complicated things. One is play text 40, which is the thing that runs the play field. That has some complexity to it. The thing that probably has the most complexity is map hires 3. That is here. Yeah. So that deals with this ridiculousness of trying to put 7 pixels into the space of 4 bytes. And so what I actually did in the end of here is I just draw things in 14 pixel groups. So every map bit, every map byte accounts for 2 pixels in the display, and so I take 7 map bytes and I display a 14 pixel chunk, and so I just draw every 14 pixels here. I do not try to address individual pixels. Even when I'm trying to update the map, I just figure out which 14 pixel group it's in and then redraw that. Okay, anyway, that's good enough. I will leave it here and toss to me on Zoom.